Let's continue from what we have last week. Last week I start a bit with notation on factorial, permutation, and combination. Now, today I will go over the rest of this 4.4, and I will give the theory first. The theory is on three techniques, three basic techniques on counting. And that consists of first fundamental theorem of counting, or simply counting principle. The second is on permutation. And the third one is on combination. Now, last time we did learn to compute permutation and combination, but this time is the explanation on when we will use permutation, when we will use combination. Okay. Now, these three basic techniques should be considered as a tool, not as cases. In other words, we may have a case later on in which we need to use more than one tool. Okay, let's start with first one, counting principle. And I will explain it in, for each of this topic here, I will explain it in 4 steps. First one, we will see, no, I don't want to use the category. I can use A, B, C here. And this is one. The first step is on what's the situation. And what situation we will use counting principle. That's if we have the simplest case, if we have 2 boxes. Box 1 consists of X items, and box 2 consists of Y items. Yeah, I use the word box here, but it's basically category, groups. Okay. For example, suppose I have 2 boxes. Box 1 consists of 3 pens, and then box 2 consists of 2 erasers. And then second, the action. What do we need to do in that situation? We will select one item from each box. Give me a second. So going back to this example, what we will do in this situation, we are told to pick one from the first box. We need to select one pen, and then from the second box, we'll select one eraser. And the question is, how many different pairs possibly get or possible? How many different pairs possible? How many different group of pen erasers we can get? Okay, and then the solution is it will be X, Y pairs. So going back to our example, if I need to select one from three pens and then one from eraser, one from each box, then how many different pairs can we get? The answer here, it will be 3 times 2, which is 6 pairs. Okay. Now, here's the thing though. Here's the thing. The reason I explain it in these 4 steps because of the following. We are given a situation, and it is possible in future we are told to do other type of action, not this kind of action. Okay, so in this situation, we have 2 categories. Of course, in general, later on, we may have more than 2 categories, more than 2 boxes. But in that situation, we are still told to select one item from each category. And the question is, how many different groups we possibly get? Okay, and the solution is we actually multiply them. Okay, if we try to picture the situation, the way it is being done, the selection being done. Suppose the first choice of pen, we have 3 possible pens to select from. We have pen 1, pen 2, pen 3. Give me a second. Yeah, so suppose we have one of these selections here. So we can choose the first pen or the second pen or the third pen. And then from each selection of pen we made earlier, we have 2 possible erasers to choose from. So when you choose one of the pen, you will get into one of the first pair, the first 3 pairs. Okay, you can go either you get this one or you get this one or you get this one, either one of them. Okay, and then once you get a pen, let's say you get pen 1, right? Then you will choose one of the erasers. You have either this one or this one. Okay, so in total, you will see that you have 6 possible pairs to get at the end. And those are pen 1 with eraser 1, pen 1 with eraser 2, or pen 2 with eraser 1, pen 2 with eraser 2, pen 3 with eraser 1, pen 3 with eraser 2. Either one of these three. I mean, either one of these 6. Okay, that's the counting principle. Now we can actually use this in other situation. For example, let me give more example. Okay, let me give more example. Suppose, for example, we have ATM pins. ATM pins consists of 4 digits. ATM pins consist of 4 digits. Now, how many pins available if, let's say part A, there is no restriction. Like you can use any numbers. You can use any numbers for these 4 digits. Then for the first digit, you have how many choices? How many numbers do we have? In a digit, we can choose from 0 to 9, right? We can choose from 0 to 9. And it means we have 10 choices, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 choices for the first digit. Is it okay? Now, once we select one number for the first digit of our ATM pin, then we go to the second digit. There's no restriction, so we still can use the number we chose earlier, right? Okay, so there are 10 then, and then the third place there are 10 more again, and then the last place we still have 10. So in total we have 10 to the 4th or 10,000 pins available. If there's no restriction, then there are actually 10,000 pins we can choose from. Now, what happens if we have some restriction? That is, let's say, the first digit can't be 0 or 9. The first digit cannot be 0 or 9. So only 1, 2, 3, 4, 5, 6, 7, 8. Now, so originally we have 10 possible choices. Now we only have how many? I wonder how many of you listening to me. If we cannot use 0 or 9, so you see we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But we are not allowed to use 0 or 9. Okay, so how many options we have for the first digit? Only 8. Is it right? Only 8. Then, so in the first box here, you can see the first digit as your first box. Okay, in the first box, we have only 8 choices. Now then, how about the second place? Is there any requirement we need to satisfy for the second place? It doesn't say that we are not allowed to use the same number again. It doesn't say that we cannot have repetition. So the second digit, we still have 10. right? Go back. We can use any numbers from 0 to 9. And then 10, and then 10. We have 8,000 pins if that's the restriction. Okay. Now, what happened if, maybe I add more, what happened if the restriction is no repetition? So the number you use cannot be used anymore. Yeah, no restriction of what kind of number you can or you cannot use, as long as no repetition. Then if I start from the first digit has 10 possible choices, right, from 0 to 9. But whatever digit you select for the first place, you cannot use that anymore in the second place. So your second place, you only have 9 numbers to choose from, excluding the first number you already used in the first digit. Okay, that's why it becomes 9. Okay? And then in the third place, the third digit, how many choices you have then? Only 8, right? Because you already have 2 numbers being used in the first 2 digits that you cannot use anymore. Now with the same logic, then the fourth digit, you have only 7 choices. Okay. Now, later on in my probability part, I need you to write this coding first. Instead of giving me the answer 5040, instead of giving me 5040, I need you to give me this coding first. Okay, I need you to give me this first. Okay, that's more important than your final answer 10,000, 8,000, 5040. I want to see the notation first. Okay, by the way, this is also what we use if somebody asks, suppose for example, California license plate. For cars has the configuration letter. No, I'm sorry. It should be numbers, huh? So it should be digit, and then letter, 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 and then digit, 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 digit. Is it right? Look at your license plate. Yeah, the regular license plate. The regular license, not the specialized one, the regular one. Now then, the question is how many license plates available if there's no restriction. Then for the digit, there are 10 possible choices. Yeah, you may say, but Thomas, we are not supposed to use 0 for the first place, the first digit. I know. But right now in this question, they don't tell us such restriction yet. Okay, they don't tell us such restriction yet. So even though we know that it should be digit followed by 3 letters followed by 4 digits. Actually, hold on. Is it followed by 4 digits or 3 digits? Suddenly I forgot. Followed by 3 digits or 4 digits? The last 4. I think followed by only 3. Is it right? Only 3. Thank you. Yeah. Suddenly I kind of like, sorry for my brain fart. So only followed by 3 digits. So 1 digit followed by 3 letters followed by 3 digits. Okay, but it doesn't change the technique. Okay, it doesn't change the technique. It's I just try to be more realistic, at least for the license plate case here. And then how many letters do we have in our alphabet? How many letters we in the alphabet that we know that we can use here? There are 26. So for the first letter, there are 26 possible choices, followed by the second letter, which is the third character, 26, and then 26, then 10, and then 10, and then 10. Now, sometimes the number is so big such that if you start using calculator, the result is kind of hard to really understand, just simply because the number is so big. That's why I want you to first write uh, the notation first. Okay, this would be 17576 followed by 4 zeros. So there are 175 cars, license plates for cars available. Now, of course, in reality, it is true. There are restriction on the license plates. For example, as I know, the first digit cannot be 0, for example. And then the letters they don't use O. As I know, they don't use O. They don't use S also. They don't use I either. Maybe, I don't remember. Honestly, I don't remember. I don't know. I don't know. But using those restrictions, then we will see that the number of license plates for cars available for sure is less than this number, right? Because even with the restriction, at most you have 175 million something, right? Now, so if you have extra restriction, then the number of license plates available for cars must be less than this, right? Okay. Now, let me stop here, and then I go on to the next technique of counting technique. Later on, we will actually put things together, doing problems from our book. And when I look at our textbook, it seems like we don't have enough problems from our textbook. And there are some very, very good problems available out there that's very useful, very uh, very useful for our life, that our textbook does not cover. And honestly, when we first used this 13th edition, I was very surprised because in the 10th edition, of this textbook, uh, this section is long, 4.4, counting technique is a very long section. Okay, but then in the 13th edition, they didn't ask more than 40 problems, much less than 40 problems. While in the 10th edition, they have like around 50 problems. So what I may do later on, I will take pictures from the 10th edition that we use in our exercise. Okay. It's not that I say a lot of problem is necessary. Okay, it's understanding is more important. Understanding is more important. But you will see what makes this section not only long but difficult. What makes this section is long and difficult is that the application into real life has so many variations, such that what I really need to train you is not really about uh, how to use these 3 tools here, but more about how do we know which tools we should use. Okay, and who knows, we have more than one tools we need to use at the same time. Okay, so it is possible later on we will need to use tool number A and tool number C. That's possible. That's possible. Okay. But definitely with the number of problems in our textbook, it's definitely not enough. Definitely not enough. Okay. I can write 100 problems today and teach you 100 problems today, and tomorrow I can come up with another 100 problems totally different, but the underlying concepts are exactly the same, such that if I only teach you like around 30 problems to do, even if I do all the problems from our textbook, okay, you may not see the implication on how to use them in wider sense. Okay, that's why I say that this section will be long, and there's a chance that I use all 4 hours, 5 hours just for this one section. Second, permutation. So I hope you also see that when we say counting techniques on counting principle, permutation, combination, it's more than just what situation we are in, but what situation we are in, what we need to do, and what is being questioned after our action. Okay, so the first one, what is the situation we are in when we deal with permutation? In permutation, we have only one box, only one category, with and distinct items. With and distinct items. Let's say, for example, you know what? Let me name it. Let me name my example this way. This is example A1, and then this is example A2, and this is example A3. So when I say example 1 later on, you know which example we're talking about. Okay, example B1. Suppose I have 5 letters, A, B, C, D, E. Now, if in counting principle we have multiple boxes, and select one from each box, right now we have only one box, but we have uh, distinct items, and what we will do is the action, we will select R items without replacement, means whatever item you already select, you don't put it back. Whatever item you already select cannot be selected anymore in the next selection. Okay, and order is important. Let's say, for example, in this situation here, we have 5 letters. What we will do is select 2 letters. And when we say select 2 letters, it's not select 1 letter twice. No. When they say select 1 letter twice, it is possible the repetition is allowed, right? But when we say select 2 letters, then these 2 letters has to be different. Okay? Yeah. Select 2 letters. Let's say to be a password. Yeah, of course, because it is a password, then the order is important. Okay, then the question is how many different arrangement possible? How many different permutations possible? How many different orders possible? Okay, basically, the wording implies the order is important. Okay, so with the letters A, B, C, D, E, we will select two letters to be a password. Okay, how many passwords can we make? Can be made. Okay, and then the solution is N permutes R. That's the solution. So here we have five letters, five different letters, right? Okay, and then we want to select two to be our password. Then it will be 5 permutes 2. You can use your calculator, but if you remember how to compute that by hand, you will see that's 5 times 4, which is 1. Now we may be now interested in what are these 20. When we say, oh, there are 20 possible passwords can be done, that can be made from here. What are those 20? Let's write them down. Let's write them down. Those are A, B, A, C, A, D, A, E, B, A, B, C, B, D, B, E, C, A, C, B, C, D, C, E, D, A, D, B, D, C, D, E, and then E, A, E, B, E, C, E, D. Okay. Those are the 20 two-letter passwords we can create from these 5 letters. Now, the thing is, most of the time, the questions are not, what are those passwords? Okay, no, usually the question is, how many passwords possible? Now, imagine if we are allowed to use only 2-letter password for our bank account, then somebody will just drain it within 1 hour. Give me 1 hour, I can drain it, right? Okay, that's what. So if somebody say, "Oh, you know what? I can't really remember my password for my bank account," right? Consists of how many letters, okay, or your email or your Facebook account, okay. Why they don't allow 2? If they allow only 2, then I can. It will be easy for me to remember. Yeah, if it is easy for you to remember, it will be easier to catch also for somebody else, right? Okay, right? 20, with these 20 possible passwords, give me 20 minutes. I can get in there, right? Okay, and then it will defeat the purpose of having a password if it's so easy to get in, right? I mean, I don't need to guess. In this case, I don't need to guess. I just try them one by one, right? Okay. Now, the other possible questions are, example, the pool. Let's say we have 10 people in a group. Okay, me decides decide to select chair, vice chair, and treasurer. Usually because the number of people in that group is so small, then they don't need to select one special secretary. Maybe instead of vice chair, let's call that secretary. Okay, with 10 people in the group, they decide to select a chair, secretary, and a treasurer. The question is, how many different ways and this leadership structure done, selected. There are 10 people and you need to have a chair, a secretary, and then a treasurer. Okay, so that will be 10 times 9 times 8, right? Which is basically 10 permutes 3. That is 10 permutes 3. That's 720. But the issue is not 720. The issue is how do we see this as 10 permutes 3? You have 10 people, okay, to put into 3 different positions, okay, into 3 different positions, and they are different positions, such that Thomas being a chair is different leadership structure compared to if Thomas being a secretary. Okay, it's different from if Thomas being a treasurer. Okay, now here's the good news. Good news. All permutation problems can be done by counting principle. All permutation problems, all problems that you can handle by permutation must be doable by counting principle. So what is the purpose for us learning permutation problems? It's more about providing us some shortcut. It's more about providing us some shortcut. Okay, so imagine if I change this example V2, instead of 10 people, let's say we have 100 people, and then you want to select a group consisting, let's say, 10 different positions. Like if you have 100 people and you want to put these 10 of them into 10 different positions, that would be 100 permutes 10. Okay, instead of doing 100 times 99 times 98, you get distracted and discouraged by the time you really finish writing it, right? But if we see that from a big picture, oh, you know what? That's actually 100 items permutes 10 of them. Okay, likewise, if you look back to this number, example V2, it's basically 10 permutes 3. Okay, but the one I say as a good news here is even if you do it one by one, it's still okay. It's still okay. Now that's why this is where the first time you may get some confusion when you do problems later on. Thomas, how do I know when I can use permutation? How do I know when I can use counting principle? Okay. Now, my advice for you is try to do it with counting principle until you realize it's simply a permutation case. Okay. Now, in other words, permutation problem, tool B is part of tool A. Okay, so every permutation problem can be done using counting principle, but it's not the other way around. Not all counting principle problem can be done using permutation. Okay, not all counting principle problem can be done using permutation. Okay, now let me do one more example. Another example, example B3. Let's say there are 30 paintings to the to exhibit. That you will put it in a show or put it in a museum. Okay, but only let's say 15 to put on the wall. Okay, now the question is how many different placements possible? So you have 30 paintings, okay, but you can only put 15 of them. And of course, when you put it on the wall, let's say this is the wall, okay, and then you put a painting here, you put painting here, okay. If you reverse the order, you count it different placements. If you put them in different order, then you count it as different placements. Now the question is then, how many placements possible? How many different ordering possible? Then instead of saying 30 times 29, 10 times 28, and so on and so forth, we better just think, oh, there are 30 paintings, and then I will have 15 of them put in order. Okay, now the thing is, even this, when you use your calculator to compute, it may be such a big number. It may be such a big number. You get this thing, 2 point, if I use my calculator, maybe I use my calculator here and then screenshot it. Give me a second. You can see my notes, right? Because I purposely turned off the video for my face. You don't need to see my face. I want to clear this. Okay, so 30 math PRB NPR 15 enter. Now you see this number here? Maybe I screenshot that. The thing is, when you see that, do you know what it means? We have issue here. What does this mean? Now, that's actually as the way our calculator write it in scientific notation. Okay, this actually means 2.028432049 times 10 to the 20 times 10 to the 20, which means after this 2 here, after this 2, it is followed by 20 digits. And the 20 digits that you see after, the digits that you see after now, above, are only part of it. Are only part of that. But then we have more digits there. Should be 20 digits. 16, 17, 18, 19. There are 20 digits here. That's what it means. Okay, so you see what I said earlier. Sometimes the question is not about what are those different placements, but it's more about how many different placements possible. Okay, so later on when we try to get into probability, then it is of course very unlikely that the first 15 paintings happens to come from the same painters, for example, right? Okay, if you have 15 two painters painting these 30 paintings. Okay, 15 of them Thomas painted, and then the other 15 somebody else painted. With so many possible ways to put these 30 paintings on, it is nearly impossible that all 15 of them from Thomas and happens to be in the order that I paint them. No, it won't happen like that if we get into probability later on. So it starts with how many possible options there, right? Okay. If it is randomly done, there should be this many ways to do that. Okay. If it is randomly done, there should be this many ways to do that. And to have them show in very particular order is not correct. Okay, now in this situation, I may still ask this question though, but in this situation, in my test, I want you to just write it this way. Okay, now the thing is, if you try to write it doing it by counting principle, you will type 30 times 29 times 28, and by the time you're done, you will look at these kind of numbers and you say, Thomas, your question is error. It's an error question. Okay, I did ask some wrong question in the past, but that's not the first thing you have in mind when you see something wrong. Okay, instead of asking what's wrong with the question, ask yourself first what's wrong with the answer. Okay, now this is the type of question in which if you use counting principle, even though that's correct, okay, but your calculator cannot handle it, and because I would like to see the notation more than just the numerical result. Okay, so 30p15 here, when I ask you this, it's more about, do you know what do we need to do? Okay, next, the third one. Now, if you think we are not really clear yet right now about those counting principle and permutation, be patient with me. Let me finish this combination first. And after some examples on combinations, then we hit questions from our textbook. Okay, so after I'm done with this part C, I will give myself a little break. Okay, and then after that we do problems from our textbook, and then after that we get a little break, and then we do problems from other textbooks. Okay, this way I'm not trying to just give you the different examples. It's more about to expose you with how we see which tool to use instead of the like doing a lot of problems. Okay, next one, combination. Combination and permutation are very, very similar. Very, very similar. The situation we start with is exactly the same. The situation, you have one box or one category to choose from with an distinct item. Okay. Let's say, for example, our example C1, we have those 5 letters again, A, B, C, D, E. The action, we will select R items from those N without replacement. So up to here, it is still exactly the same with permutation. It is still exactly the same with permutation. You have one box with N distinct items. You select R items without replacement. Okay, now the difference is now order is not important. In permutation, order is important. Okay, suppose you have a password and your password is God. Okay, then if somebody use password DOG, of course not the same, right? Okay, I love both of them. Okay, but when you use them as a password, if one works, then the other will not. Okay, now, however, when it comes to combination, the order doesn't matter. It's like when you try to use what you call that? What kind of locks? Mm, there are some kind of like locks in which the order doesn't matter. Okay, yeah, but as a password, of course, these two words are not the same words. Okay, they are the same combination, but they are not the same permutation. Okay. The third one, what's the question? Question, how many different sets possible? The word set implies the order doesn't matter. Same with the word group. Okay? Or if they are nice, they will say different combinations. Even though I have to admit, there are some situations the word combinations being used in our real life is not exactly the same with the word combination we use here. Okay. I mean, technically speaking, the word combinations does not imply order. That when I say I combine my, when I say I combine my Coca-Cola, and my root beer, right? Doesn't matter which one you put into the into your glass first, right? That's what the word combining means. Okay, until somebody tell you further, when you're combining, you need to do it in this order, then you don't call that combination anymore. Okay, okay. The word combination in itself actually does not mean any, doesn't have any sense of ordering. Okay, but again, in real life, that could mean something else. Okay, when it comes to communications, different people may have different understanding with the word combinations. However, in our class, the word combination implies the order doesn't matter. Okay, now step 4, the solution, it will be NCR. Again, so last week I taught you how to compute NCR. Right now, I teach you when to use NCR. Okay, now suppose I have these 5 letters here. Okay, and then select 2 letters. Select 2 letters. Order is not important. And how many sets of 2 letter possibly need? The answer will be 5 combination 2, which is 10 sets. Notice that my example C1 is very similar to my example B1. The difference is, in example B1, the order matters because you are writing a password. You are creating passwords. So the order matters. Okay, now here, you just need 2 letters. Orders doesn't matter. Okay, and according to our computation, we have 10 sets here. Okay, now the thing is, what are these 10? Okay, what are these 10? Now these 10 are, let's list them, okay? If I select 2 letters from these 5 letters, what are the possible outcomes? AB, AC, AD, AE, BA, but hold on, BA and AB are actually the same set because contains the same 2 letters. Okay, it's already counted as AB earlier. Okay, remember order doesn't matter. Okay, so letter AB and letter BA are the same letters, the same combinations, the same set. Okay, why? Because order does not matter. Okay, I continue. BC, BD, BE, okay. CA. Oops, CA already counted here. CA already counted here, right? That's why I should not count it anymore. CB, hold on, CB already counted earlier, actually next door, right? They are the same, they consist of the same letters. They consist of the same letters, just different order. But for us, order doesn't matter, right? So I should not count CB as if it's different set from BC. And then CD, CE. Then DA, oops, I already have DA. DB already have. DC already have. DE is new. Oops. DE is new. This already counted earlier. And the last set, everyone already counted. EA, that's the same to AE. EB, that's the same to DE. EC, that's the same to CE, and ED is the same to next door. Okay, so from here you see what are those 10 that we said earlier. Those 10s refers to these 10 possible sets of two letters. These are the 10. Okay. Now the thing is, of these three tools, counting principle, permutation, and combinations, the ones show up in our real life, strangely. Of course, each one of them a lot. I mean, you can pick a lot of, you can find a lot of applications for each one of them. Okay, but you will see in my class, even though I still ask problems about counting principle and permutations, you will see the one that you get trouble with a lot more are the is combination case. Okay, so you will see it will feel like we have more combination problems, while actually it's I focus on that because that's the one harder to see. It takes more training and to see or to understand that it is actually we need to use combination. Okay, now on the other hand, I said before that what the tools that I give you here are very applicable in our real life. Okay, and of course combinations are, it's not just about letters. I'm about to show you two or three more examples that has the same questions, 10 sets. Okay, but the questions actually very different. Maybe I say it this way. I can create a problems in which you require to use combinations. Okay, that looks very, very different from whatever type of combination problem you saw before. Yet the underlying concepts are exactly the same. Okay, you see this example C1 is like choosing two letters, right? Who gonna do that in their life? I mean, nobody do this for a living, right? Okay, I mean, you do this example C1 for fun, only for as an example. At most, we say we do it for fun, but nobody will live from there. Okay, so I understand if you then say at this point, Thomas, why do I need to learn this? I will never use this anyway. I understand. Okay, but this is the foundation for future examples. You will see examples later on at which that not only you will do this for a living, okay, but because you don't know that, you don't have living to live from. Okay, let's see. Example C2. There are 5 points on the circle. Let me create a circle. And 5 points on that circle. A chord is drawn using 2 points as endpoints. uh, on the circle. So basically, I need to explain first what is a chord. A chord is a line segment connecting 2 points on a circle. Now that's a chord. Okay, this is also a chord. Basically, any line segment connecting 2 points on a circle is called a chord. Now, then the question is, how many chords can be drawn using these 5 points? Now, then you may think, oh, there are only 5 points, so let me just draw it one by one. So far, I have 1, 2, 3, 4 with this, 5, 6, 7, 8, 9. Is it only 9? How do I know how many I'm supposed to have? How do I know I don't miss any? That's why you need to compute instead of drawing the lines. Okay, 10. How do I know I can stop at 10? There should be only 10. If you don't have this skill, you can draw it and still question if you already drawn all of them. Okay. So how do we know how many we have? Instead of answering how many chords right away, ask yourself, if you do it by drawing, how do you know there should be that many? If you draw it, right now you draw, you get 10, right? How do you know that there should be only 10? How do you know you don't miss any chord? Thomas, just look at that. I don't miss any. Okay, fine. Then let's make it 50 points, right? If you have 50 points on the circle, how many lines can you draw? Oh, Thomas, you just try to make it hard. Hey, welcome to life, dude. Life is hard. Okay, if life is easy, nobody have depression, right? In fact, because life is hard, then you come back to school. Don't you think so? Right? Okay. Right? We learn the skills that we need to apply in our life. Okay. Okay. We want to learn hard stuff. Okay? Don't be discouraged with hard stuff. Okay. You can uh, you can have you can have a degree that you can never apply. You know what? Let me stop here for a little bit. Let me stop here for a little bit. Now, in this example here, how many chords can be drawn using these 5 points? We know it's 10, but how do we get that 10? How do you know 10 is all we need? Okay. That's because we know we have 5 points and each chord takes 2 points, 2 different points. Each chord, each chord takes 2 different points. Right? Each chord takes 2 different points. So the number of chords is equal to the number of different pairs we can get, right? Okay. Now, if you name these points A, B, C, D, E, for example, then the number of chords is equal to the number of different pairs of 2 letters you can get. And all of a sudden, you see how this example C2 related to example C1, right? Now, the thing is, the question is not what are those chords, it's not what are those different pairs, it's just how many of them. If you cannot even tell how many are those, I don't need you to list them. Like you don't even know how many. How do you know when to stop? Okay. But Thomas, can I just draw it one by one? You can, go try. And then in your test, I make it 50 points instead of only 5 points. Right? Oh, Thomas, you just like to make it hard. No, I'm not trying to make it hard. No, I'm trying to make you learn what you're supposed to learn and don't shortcut it. Okay? Don't try to be too. I need you to be creative. Okay, but be creative based on what I teach you, not based on what you can avoid learning in my class. Okay? Is that all you can say, Thomas? No, 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 no. I said that I have 4 examples with exactly the same answer, right? Okay, I will give you those 4 examples. Oh, more things to say that when you draw the chord here from one point to another point, it doesn't matter you draw it from which point. As long as you have 2 points, when you draw the line segment from one to the other, that's the same line segment you will get if you draw it the other way around. Okay, so when the number of chords here equals to the number of pairs, and that number of pairs doesn't, the order doesn't matter in those pairs. More. Example C3. Example C3. 5 people shake each other's hand. How many handshakes? Handshakes happen. And then, yeah, you will see, oh, there should be 10 handshakes happen. Why? 5 people, every handshake takes 2 people. Every handshake takes 2 people, and the order doesn't matter, right? When I shake your hand, it also implies you shake my hand. You cannot say, Thomas, you're the one shaking my hand. I didn't shake your hand. Right? Once the handshake happens, it happens. You cannot say you are the one doing it to me. I didn't do it to you. Right? Okay. And we consider uh, 2 handshakes different if it involves uh, 2 sets of 2 different people. A shaking hands with B is different from A shaking hands with C. Now all of a sudden you see the circle, right? How many handshakes can happen? One, two, three, four, five, six, seven, eight, nine, 10. Right? But you see that in this example C3, the question is a lot shorter. The question is a lot shorter. They don't even tell you what are those 5 people anymore. They don't. We don't need to know who are these 5 people. You just need to know there are 5 people. Okay, you don't need to know. Oh, it's Thomas and Kobe Bryant, and then Tim, and then Marissa, whatever. No, no. You just need to say 5 people. They just shake each other's hands. How many handshakes happen? Okay. You don't like long problems, right? But even when you have short problems, do you understand what actually happened there? Sometimes The problem's too short that they need to explain more. That's why it becomes longer. Okay, so don't be too discouraged when you see a long problem like a paragraph consists of 10 sentences. I of course I avoid that in my test, okay, because I don't want you to waste your time in reading, okay. But at the same time, I need to have a clear question, right? Okay. Now, this if we have 5 people shake each other's hand. Okay. Of course, last year handshaking is not important, but right now with this pandemic, handshaking is actually being discouraged. Okay, not being banned yet, but it is being discouraged. Okay, but then imagine if you have a room of 100 people, not social distancing, and they do handshake. Okay. You want to do tracing, contact tracing for all these 100 people, right? How many handshakes happen? And for that handshakes to happen, how much time they need? If each handshake takes 5 seconds, okay, and they all this 100 people get in the room only for 2 minutes, then how many handshakes should happen like that? Okay. Now let me explore this even further to example 4. Example C4. 5 NBA teams who play each other. Our Lakers going to the final, right? Okay. Now then, once we say that Lakers go to the final, then how many games have they played since the very beginning of this season? Can you imagine? Right? Okay. Now, suppose we all have only 5 teams to play each other, then how many games should we play? Will be played? Of course, you will not say, oh, there are only 6 games. No, it won't be. It won't be, right? Okay. So how do you know it's 6 to start with, right? Okay. Oh, you know what? Just once you know how many games will be played, then you can do the scheduling, right? Okay. Once you do the scheduling, then you know how many places you need, or at least how many days you need to let these 5 teams play each other. You don't make these 5 teams play each other on the same day. That would be too much for any one of them. Right? I mean, trust me, no player's gonna do it, right? No players are gonna do it. How many games should be played? That will translate into the scheduling later on. Okay, if you schedule too many days, then the NBA as a franchise will lose money, right? Okay, but if they schedule too little, then some teams will not play and they will file a complaint, right? Okay, now how many games should be played? Well, each game takes 2 teams, right? So how many different sets of 2 teams necessary? That will be the number of games should be played. Okay. Now these are 4 examples that give you exactly the same answers. Okay. All of them very different from the other. Okay. Example 1 about choosing letters is of course not a geometric problem you have in C2, and definitely not a uh, social distancing problem you have in part C, number 3. And of course, it's not a sport problem you have in number 4, example 4. Okay. Now, the thing is, we can have more variations from here. Suppose I go back to this C2, example C2. If there are 5 points on the circle and the chord is drawn using 3 points as endpoints, how many chords can be drawn? And I said earlier, yeah, you can easily change it to 50 points and then you don't know what to do. You can draw and you still lose counting, lose count, right? If you try to draw it one by one and then count it, right, you will lose count, trust me. Okay, but Thomas, that's because you use big numbers. Okay, let me not use big numbers. I will use still 5 points on the circle. Example C2 star. There are 5 points on the circle. How many triangles can be drawn? Of course, when you draw a triangle, you need only 3 points, right? Can be drawn using 3 points as the vertices. So if you have that circle with 5 points, I still draw it so that you can see one example of a circle. Okay, so I draw it here just to give you an illustration. So this is one triangle. This is one triangle. If you use 3 points on the circle as the vertices, then you can draw a triangle, right? Now the question is how many triangles can you draw? How many different triangles can you draw? Now trust me, even if you try to draw it, you will lose count. Even if you try to draw it, you will lose count. But then if you think about it, okay, the number of triangles is equal to number of triangles is equal to the number of sets with 3 points. How many groups of 3 points you can select from here? And that's basically 5 choose 3. Which if you use your calculator, you will see that's still 10. Happens to be the same. 10 triangles. You can draw 10 triangles using any 3 points of these 5 points. Then I can go on how many quadrilateral. Quadrilateral is the figure consists of 4 sides and therefore comes from 4 vertices. Then how many quadrilaterals can we draw using 4 points of these 5 points on the circle? That would be 5 choose 4. Okay, now is 9:57. Let's take a little break. Okay, let's do problems from our textbook. This is the problems I screenshot from our textbook section 4.4. Okay, I think I will do even numbers only so that you have odd numbers to work on. And feel free to ask me questions either by email during the week or during my office hour. I prefer by email though. Okay, sometimes if you get stuck, it's simply because you need a little insight. Okay, let's start with number 2. New Jersey Pick 6. In the New Jersey Pick 6 lottery game, a batter selects 6 different numbers, each between 4 and 49. Winning the top prize requires that the selected numbers match those that are drawn. So you have number 1, 2, 3, all the way to number 49, right? You will select 6 from here. You will select 6 from here. Now let's see how many ways can you do this. Now, notice that you will select 6, but the order doesn't matter. Then how many possible selections you can make? Do you use permutation or combination?
Combination.
That will be combination, that's right, because you will select 6 items from only one box consisting of 49 items, right? So you have a box of 49 items, you will select 6 from there, and the order doesn't matter. So yes, that falls into combinations. There are 49 combinations, 6 ways to select. That also implies there are 49 choose 6 possible outcomes, right? So if we go on further asking what is the probability of winning the top prize, what is the probability of winning the top prize, then that will be only one of those possible outcomes. Right? Only one of those possible outcomes. Then if I use my calculator, 49 combination 6. I'm sorry. 49 math, PRB, NCR, enter 6. That will be 13 million 1 over 13 million 983,816. So the probability that you randomly select 6 numbers and that number is the one match those are drawn is 1 over this. You know what? Let me put this in a circle. I will come back to this question later on and elaborate that more. Okay. The thing is, New Jersey Pick 6, I believe, is a real game being played there. Okay. So right now we just asked what is the probability of winning the top prize. Now in reality, that's not the only prize though. You still make some money if your selection, you select 6 and 5 of them match. If you select 6 and 5 of them match, you still get some money. I think if 4 of them match, you still get some money. Okay, and we will look at those cases later on. For now, we can only answer of those 13 million some possible outcomes, only one of them match all 6. Okay, but again, we'll come back to this later. Number 4, a typical combination log uses 3 numbers, each between 1 and 49. One from 0 to 49. From 0 to 49. So I imagine if you have a log up and then the numbers here. Actually, the TSA log, if you go travel by plane, then you have TSA log, right? It's from 0 to 9. This one is from 0 to 49. Okay. Opening the log requires entry of 3 numbers in correct order. Is the name combination log appropriate? Well, because it will not be. It will not be. Because, hold on. Can you repeat the number you use here? Let's say you have, for this one, the option is from 0 to 49, right? 0 to 49. And this one also 0 to 49. And this one also from 0 to 49. Oops, 0 to 49. Now, can you repeat the number you use? You can just use 0, 0, 0 if you are that lazy, right? Okay, you can repeat. So it is not correct to assume that what you will use is combination. Of course, in real life, they still call that combination law because it combines some numbers, right? In that sense, they combine some numbers, but not in the sense that repetition is not allowed. Okay. In reality, this lock allow repetition. You can have 007, right? You can have 007. Okay. Now, knowing that you are allowed to have repetition, then how many possible quote unquote combination can you make, even though the word combination there is not appropriate? Not in, I should not say that it's not appropriate. I should say the word combination there is not in the same understanding with our word combination we learned in this section. Okay, but how many possible outcomes there? How many choices you have here? 50. From 0 to 49, there are 50 choices. So for the first place, there are 50 choices. The second place, there are also 50 choices. And the third place, also 50 choices. Right? That's 125,000 possible quote-unquote combinations. Okay, let's do number 6. Let's do number 6. Social Security numbers. A Social Security number consists of 9 digits in particular order and repetition of digits allowed. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and repetition allowed. Okay. Now, and then after seeing the last 4 digits printed on the receipt, so you happen to know somebody else's Social Security number, the last 4 digits only. Actually, with these last four digits only, you can do so many things already on that person. In other words, even when somebody only asks you the last 4 digits of your Social Security number, make sure that person asks for a purpose that you intend. Right? For example, when you call for your credit card, let's say your credit card happens to be blocked, and then you call in, you want to unblock that. They may ask you some personal problem, right? And one of them usually the last 4 digits of your Social Security number. You know, okay. In other words, if somebody else knows the last 4 digits of your Social Security number, that person may gain access to your account. Okay. My health insurance I get from the district. We have this some kind of a program in which that basically at one point I need to call the company that take care of my health expenditure, and they asked me my Social Security number, and I was like, do we need to give that? Can I just give you my membership number or my employee number? They say, no, we need your Social Security numbers. I say, can I just give you 4 digits? They say, no, we need all 9 because we need to make sure it's really you. I said, but how do I know that you will not abuse that? Right? And then the person say that, well, if you think we will abuse it, then why do you call to start with? You know, oh, okay, then what I say, well, you know what, I will call you back. So I call my campus first to confirm that that's information that this company will need, you know. And once they confirm, then I call back that company and give them my 9 digits. But even 4 digits right now is enough to actually take care of your bank account. So please be careful. Okay. Of course, when you open a bank account, they need the full 9 digits. Okay, they need the full 9 digits. Unless you are international student that you don't have Social Security number, then they will need your passport, right? But when you open an account, they need 9 digits. For you to change that, they may need only 4 digits, especially when you call in. Okay, so take care even if it's only 4. Now, continue with this question. Okay, if you randomly select the other digits, what is the probability of getting the correct social security number of the person who was given the receipt? In other words, you just need to guess the other 5. We just need to guess the other 5. What is the probability you get it right? Then you see how many possible choices there. That's 10 times 10 for the second place, and times 10 for the third, times 10 for the fourth, and times 10 for the fifth. Okay. In particular order, so the order is important and repetition is allowed. So there will be 100,000 possible outcomes. The probability that you guess it right one time, you guess it one time, you guess it one time and you get it right away will be 1 over this 100,000. Of course, if you give me 100,000 chances, I will for sure get it right. Right? Okay? I will for sure get it right if you give me 100,000 chances. But if you give me only one chance, then my probability of getting it right will be 1 out of that 100,000 possible outcomes. Number 8. Soccer shootout. In soccer, a tie at the end of regulation time leads to a shootout by 3 members from each team. How many ways can 3 players be selected from 11 players available? So you have 11 players. So this is the soccer, the World Cup soccer type. Okay, 11 players. And you will select 3. Now, the first question, how many ways can 3 players be selected from 11 players? That will be 11 combination 3. 11 combination 3. And then you use your calculator for that, right? How many ways can 3 players be selected from 11 players available? The answer will be 11 combination 3. Now then, for 3 selected players, so if you have 3 players, how many ways can they be designed as first, second, third? Okay, so you start with these 3 players that you already select. Okay, how many ways can they be designed as first, second, third? That will be the first place 3 choices, the second shooter is 2 choices, and the last one is 1. Okay, so that's equals to 6 for a 3 selected players. Once you already select 3 players, then there are 6 different ways for you to design them to be the first, second, or third shooter. Okay, but in total, there are 11 permutes 3 ways to select 3 players as shooter 1, shooter 2, shooter 3. In that order. Okay, so in fact, how do you select 3 players to shoot in that order? One way to do it is actually you randomly select 3 players first. From these 3 players, then you arrange them. Okay, that's how you actually get the permutation. Okay, that's how you actually get the permutation. Okay, so the answer for the yellow one is 11 combination 3. For the blue one, because they say for 3 selected players, for the blue one, once you already have those 3 players, how many ways can you decide them to be the first, second, third shooter? There are 6 ways. Okay, now, so if I tackle this problem starting from 11 people, how many ways can I select 3 shooters to be the first, second, third? That will be this many ways. That's for number 8. Let me see more questions. Basically try to do all even numbers here. Go on. Number 12. A survey with 12 questions is designed so that 3 of the questions are identical and 4 other questions are identical. How many different ways can the 12 questions be arranged? So you have 12 questions. 3 of them same. Let's call it one group. Okay, and then the other 4 another same. Okay, so far there are 7 questions, 3 of them the same, the other 4 also the same group. This is same, this is same, and then we have one questions. Okay, the total of 12 questions, right? A total of 12 questions. How many different ways can the 12 questions be arranged? How many ways these 12 questions be arranged? How do we attack this problem? This requires us to do multiple steps, but this is the way I see. This is the way I see. Okay, this is the way I see. This group here can be seen. How can you rearrange this group here? We have 3 factorial ordering. 3 times 2 times 1. We have 4 factorial ordering here. Okay, and then each one of these are the same. I mean, different question, different question, different question, different question, different question. Okay, now, so this is what will happen, that I will do it this way for number 12. I'll do it this way. Assume all these 12 questions are different. Assume all 12 questions are different. So how many different arrangements you have? There will be 12 factorial different arrangements. Now, then I divide. 3 of them are identical. Okay, so there are 3 factorial arrangements are the same for every one of those. And then this also 4 factorial. That will be the answer. But I don't like my solution right now because I don't really explain it that well. I don't think you understand what I'm doing here. Let me change the problem this way. We look at a similar type, maybe not 12 questions, but let me make it this way, okay?
What is that?
Okay, let me do it this way. I will start with this. Yeah, let's say I have 4 colors. I only have 4 colors here, so I have no choice anyway. That's the maximum number of colors I have. Okay, and then I want to rearrange how many different orderings for these 4 colors. How many different orderings, arrangements possible with these 4 colors? Then, because you have 4 colors, there will be 4 in the first place, 3 in the second place, 2 on the third place, 1 on the last place. So there are 4 factorial arrangements. Now, are you okay with this first? For now, are you okay with this? This takes a long explanation. Give me a second. You know what? Let me change something. To change the configuration, the position. Something to do with arrangement. Now, then I will modify the problem right now to make it this way. Suppose instead I have 2 yellow, 1 green, and 1 purple. So you see, I changed the blue color to be yellow, right? Now then the question is, how many ways can I rearrange this? How many different arrangements? The way it is being done is assuming all four are different. There are 4 factorial ways, right? Okay, but because these two here are the same colors, I can rearrange this any 2 yellow colors. I can swap them without any visible difference. Okay. Now let's actually write it down. I don't think there are a lot of. I think there are a lot of. I don't think there are a lot of possible outcomes from the one on the left hand side. Let me call them this way. Let me call them color A, B, C, D. Is it okay? Let me call them A, B, C, D. And according to our computation, there should be 24 possible arrangements. Let's write down all those 24. Is it okay? I will write down all those 24. A, B, C, D, A, B, D, C. A, C, B, D. A, C, D, B. A, D, B, C. A, D, C, B. And then B, A, C, D. B, A, D, C. B, C, A, D. B, C, D, A. B, C, I'm sorry, B, D, A, C. B, D, C, A. So far we have how many? We have 12, right? And then C, A, B, D. C, A, B, D. C, B, A, D. C, B, D, A. C, D, A, B. C, D, D, A. Oops. C, D, D, A. And then finally D, A, B, C. D, A, C, B. D, B, A, C. D, B, C, A. D, C, A, B. D, C, D, A. And you will not see anything other than this 24. So you will not see anything other than this 24. Okay. Now the thing is, in my later case here, I change one of the color, the blue color becomes yellow. So basically, if I kind of like translate that into letters, I'm actually having A, C, D right now. A, C, D. In other words, my B originally now becomes A, right? So assuming all difference now, assuming all different, now my B becomes the same A. Okay. Now what happened then? This arrangement here has A, B, A, B, A, B, like this. Okay. Each of them already have its pair. Maybe if I show it to you this way, then if I change this B becomes A, right? If I change this B becomes A, C, D will be the same to this one. Okay, and the one here, A, B, D, C, will be the same to this one. Right? Because remember, you change the B to A, right? So if you change the B to A, it looks like A, B, C. But this one will also look like A, B, C. You see what I mean? And let's say ACBD will be the same to BCAD, because if I change the B to A, that ACAD, which is the same to this ACAD. Okay, so you see that each arrangement, if all of them different, now being has its pair, has its twin in this case, because uh, the number of ways you can permute these two same colors is 2 factorial, which is 2. Okay, so if I actually list them now, I have A C D, A D C, A C A D, A C D A, A D A C, A D C A. Okay, and when I go through this list, replacing the B's by A, I will see exactly the same thing. Okay, in other words, this guy translates into this. This second column also translates into the same list. Okay, so you will end up seeing only 12 possible different arrangements. You only see 12 different arrangements. You know what? Let me go on with this. Let me go on with this. Let me go on with this. Suppose I change this here. I change the B becomes A. If I change the B becomes A, it becomes CAAD, right? Okay, and then CADA, CAAD. Oh, that's already doubled, right? Okay. So you will see that when I change the B becomes A, if I change the B becomes A, you will see this guy will be the same to this guy. Right? And this guy here will be the same to this guy. This guy here will be the same to this guy. Okay, then you will get only 6 again from there. You'll only get 6 from there. CAAD, CADA, CDAD, AA, right? And then let me go to the next line. The next column, DAAC, DACA, and then DCAA. These are all possible outcomes if you replace the B by A. There are only 12, and that 12 is basically what you get here. That's 24 over 2 factorial, which is 2. That's how we get that 12 arrangements. Now let's expand this. Then how do we do problems? How do we do problems with this? Suppose how many arrangements, different arrangements, how many different arrangements for, let's say I have A, B, C, C. So you have 9 letters right now, 3 of them A's, 2 of them B's, 4 of them C's. And then you want to rearrange these. How many different arrangements you can get? So first we assume we assume there are 9 different letters, right? There are 9 different letters. Now then, 3 of the A's can permute among themselves without change of the loop. So I divide by 3 factorials. Now then, 2 of the B's can permute among themselves. You can swipe those 2 B's and the words still look the same. And these 4 C's here can swap among permutes among themselves and still look the same word. So Thomas, which of the 3 counting techniques we actually use here? We actually use permutations. But permutations assumes all of them different, right? Permutation assumes all these letters are different. Okay. So is it really just permutation? No. It's permutation being used many times. So I use the same tool, but not only one time. You see how evil is this technique of counting? Okay, when I say basic technique of countings, right? Okay, it's just like if you use it one time, that's what it means. What happened in this question is you actually use it 4 times. Okay. Where are those 4s? First, you assume all those letters are different. So there are 9 factorial ways to rearrange them. Now, because 3 of them the same, you can permute these 3 and the outlook still the same. That's why you divide by 3 factorial. Likewise for this, likewise for this. Okay, now then how do I compute this Thomas on calculator? Now that's another story. Here's my calculator. But I would like to show you too how to use calculator for this. It's 9 factorial. 9 factorial. Right? Divided by the product of. So I need to use parentheses. Okay? I need to use parentheses. Divided by the product of 4 factorial. Times 2 factorial, which is actually, you know, that's 2, times, I'm sorry, it should be 3 on the first one, huh? Okay, wait, the last one, I do it this way. 3 factorial, 2 factorial, 4 factorial, I happen to type it in different order. But it's multiplication on the denominator, so they're the same anyway. Right? Okay, press enter. There are 1,260 ways. Now, one very well-known question for this, which shows up very often in a lot of textbooks, but strangely, I don't find it in this textbook. I don't find it. So in the past, in the previous edition, they actually have the follow. Oh yeah, they do have this question. They have this question, number 22. Let me quote it. This question is so well known that it shows up on all counting technique problems. Number 22. So all of a sudden I jump to number 22. Even this textbook say a classic counting problems is to determine the number of different ways that the letters of Mississippi can be arranged. So suppose you use all the letters from this word Mississippi as your password, right? But you rearrange that. How many different arrangement possible using all the letters in this word. So let's see how many letters there first. Me, see, uh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 letters. Okay, 1M, that one is clear. How many eyes? What the hell? How many eyes? 1, 2, 3, 4 eyes. One M, 4 eyes. How many S's? 4 S's and 2 P's. Right? Now then, the question is, if you really want to create a password from this word Mississippi using all the letters from this word Mississippi, then how many different passwords can you recreate? The thing is, some of the letters are the same. So permuting these same letters will not result in a new password. It's like if your password is Mississippi and then you say, you know what, I want to swap this S here with this S here. Okay, go ahead, swap it. It will be the same password, right? Okay, so the permutation among the same letters will not result in the same password, right? Okay, so this question actually boils back to what we have earlier. Okay, how many different arrangement you can get using all the letters in the word Mississippi? That will be 11 factorial over 4 factorial, 4 factorial, 2 factorial. That's the answer. Now the rest of that is just computing. Okay, that's for number 12. So number 12, question for number 12, actually asking about this. If you have 12 questions, okay, but 3 of them are identical. So let's say I, as a teacher, I need to ask 12 questions, but I actually only have 7 questions. But 7 is not a good number. And some of them require, I want to emphasize that some problems are so important. So I ask that 3 times and 4 times. Okay. But the thing is, I have so many students that I want to give each students different arranged problem set. Now, then how many different arrangement I can get? Okay, so my number 1 may be, your number 1 may be somebody else's number 3. Okay, but I ask these same problems 4 times. And then these same problems 3 times of these 12 questions. I just make them look different, but they are actually asking the same thing. Okay, yeah, let's say this asks about the mean, population mean, population variance, population standard deviation, okay, and then sample mean, and then sample variance, and then all this is about combination, and all of this about permutation. But permutation and combinations are actually problems that have a big application. So I ask that in different ways. But the underlying concepts are all the same. 3 of them permutation, 4 of them combinations. Okay, now you see how questions about the ordering of problems in a test actually have the same idea behind the way you create a password. And in the past, I actually asked one question that I expect each student should come up with different answers. So be prepared with this. I may be crazy enough to ask you this. No, it's not crazy. I don't want to say it's crazy. I once asked this. Okay, write your name, write your first last name, first and last name in one word. So for example, my name is Thomas Arjuna. And then how many different arrangements for all letters in that word. We can say this way. Suppose I want to create a password using all letters in my name. Then how many different passwords I can create? That will be, there are 13 letters, 13 factorial over 2H, 2 O's, oops, 2 O's, 2 A's, any else? I think that's all. Oh. H, O, A, that's it. So these are the number of different arrangements I can get. These are the number of passwords I can get using all the letters from this name, Thomas Arjuna. Now somebody have a name quite short, let's say Anna. How many different passwords can you create using this? If your name is Anna, for example, then there will be 4 factorial over 2 factorial, 2 factorial. That's 24 over 2 times 2. There are 6 ways. You want to write all 6? This is one of them. So far we have 3. A, M, and A. Oh, I'm done with this. And then N, A, N, A. Notice that I didn't stop once I was done with that 3 because there should be 6, right? Right now, I already have 6. Should I check more? No, because I know there should be only 6. Okay, so if your name is Anna, then don't try to create a password using the letters in your name. Okay, it's easy to guess. Okay, of course you don't even want, even if you do so, don't tell anybody that's what you do. Okay, yeah, don't tell anybody that's what you do. Okay, I still can tell because these numbers is actually quite a big number, right? If you try them one by one, then by the time you finish 10, you already get locked out, right? And my bank will already notify me, hey, somebody tried to get into your account, by typing in wrong passwords. Okay, but if your name is A, even if you do so, don't tell anyone. Okay. Let's go further. Let me see number 14. I did number 12 earlier. Number 14. When testing for current in a table with 5 color-coded wires, the author used a meter to test 2 wires at a time. How many different tests are required for every possible pairing? for two wires. Let me just answer right away, 10. How do you get 5 choose 2? Because every time he tested, when he said the author, it refers to himself, Mr. Triola. Okay, so when the author actually tests, every time he tests, he needs to pick 2 wires, right? Okay, 2 of these 5 color-coded wires. Then how many different pairs can he get? That's 5 choose 2, 10. We did it before. Okay, in fact, we did exactly the same thing on different problems. It's kind of strange, huh? It's kind of strange. Usually you have similar problems with different answers, right? Right now we have different problems with the same answers. Don't you think it's kind of amazing? Just think about it. Like I can create similar questions with different answers. I mean, that's a lot in math. Like when I do factoring, greatest common factor problems. Okay, I can create 20 greatest common factor problems, all with different solutions. Right now, instead, I can create 10 problems with the same solution. Which is not that common. Okay, number 16. Number 16 here. The United Fan Lines Moving Company has a truck filled for deliveries to 5 different sites. If the order of the deliveries is randomly selected, what is the probability that it is the shortest route? You have 5 sites. 5 sites to deliver. Of course, you need to go to all 5, right? And then you randomly select that. Okay, then how many routes are possible? The first place to deliver, there are 5 places, and then is repetition allowed? Is repetition allowed? Of course, no. Once you deliver to that place, you don't go to that place again, right? You're done with that place. Okay, so after you go to the first site, you have only 4 sites to go, and then after that 3, and then after that 2, and then 1. Okay, notice that that's the same to 4 factorial. I mean 5 factorial. 120 possible routes. Now, of this 120 possible routes, what is the probability that's the shortest one? Probability that is shortest, it must be one of them. Like only one of these 120. In other words, if somebody actually can go through a shortest route or to deliver these 5 to these 5 different sites, then that person must have sat down and think about which route will be the shortest before actually doing the route the delivery. Okay, not just like, you know what, I do it randomly and it happens to be the shortest. Shut up, you must be lying. No, you must be thinking about it so that you can get the shortest one, because the chance for you to get it randomly and still the shortest is less than 5%, which is very unlikely. Okay, it's a good thing though. I mean, that's a good thing. So I don't think anybody will brag about it like, you know what, I do it randomly and it happens to be shortest. No, that's silly. I will say I sat down and I get the shortest one. That's what makes me better than you. Okay, usually when people say, no, I happen to do it randomly and it happens to be that one, usually that's the bad thing happen. You know, it's like for example, what is the probability that the delivery you use happens to be the longest route, right? Then that will still be that probability, right? Okay, but that's not something to be proud of. Okay, that's not something to be proud of for that one. Okay, let's see more. How about Number 18. That's, oh, number 18. When four golfers are about to begin the game, they toss a tee to randomly select the order in which they tee off. So let's say, yeah, and then what is the probability they tee off in alphabetical order by last name? So let's say their last name start with A, B, C, and D. Now the question is, how many ways can you rearrange this? How many different arrangements for this? There are 4 factorial arrangements, but only one of them in alphabetical order. Only one of them out of 4 factorial, 1 over 24. Okay, why I kind of like do it faster now? Oh, well, because we have done enough problems. We've done enough problems, and we start getting to know the method. Okay, I think you can do number 20. Let me ask you to think about number 20 for a couple minutes. With a short time remaining in the day, a FedEx driver has time to make delivery at 6 locations among 9 locations remaining. So of these 9 locations, he has to choose 6 of them. The question is, how many different routes are possible? How many different routes are possible? Then that should be 9 permute 6, right? And then from there you use your calculator. You can also say, well, I have 6 places to go, but 9 choices to start with. So that would be 9 times 8 times 7 times 6 times 5 times 4. But this is basically 9 permutation 6. We have done number 22. Let me see, number 24. No, I don't like number 24. Let me do number 23 instead. That's a good question. I like number 23 a lot. In a second, I code it for you. And then after this number 23, yeah, after this number 23, we'll take a little break. A long break instead of the little break, the 20 minutes break. Number 23. The digital pet rock company was recently successfully funded by Kickstarter and must now appoint a president, chief executive officer, CEO, COO, and CFO. It must also appoint a strategic planning committee with 4 different members. Okay, there are 10 qualified candidates, and officers can also serve on committee. Oh wow, officers can also serve on committee. Okay, well, if we put them together later on, it may be complicated. Then, how many different ways can the 4 officers be appointed? Order is important, but no repetition. That would be 10 permutes 4. How many different ways can a committee of 4 be appointed? Well, because that's a committee, the order doesn't matter. There will be 10 combination 4. What is the probability of a randomly selected community member of randomly selecting the community members and getting the 4 youngest of the qualified candidates? So you have 10 candidates, okay, 4 of them youngest, okay, the other 6 not so young, okay. Then what is the probability of selecting 4 youngest qualified candidates? There's only one way to select that 4 youngest out of 10 combination 4. To be more precise, we get that one from selecting 4 from here and nothing from here, to be more precise. So it's supposed to be 4 choose 4 times 6 choose 0 over 10 choose 4. You have 10 members, you need to select 4 of them. That's the number of ways you can select 10 members. 10 choose 4. What's that? Yeah, let me just do it by hand. This is my 8, this is my 3, so 210. Now 4 choose 4 is 1, 6 choose 0 is also 1. So the probability that you randomly select 4 candidates and all 4 happens to be the youngest one is a very rare event. It's less than half percent. Less than half percent. Now, if that actually happens, very likely the person who did the selection purposely chose the youngest candidates. Okay? Let's see. 6. Oh, that's a good one. I didn't think of that. 26. Identity theft with credit card. Let me ask you to read it first instead of me reading it for you. There are 16 digits, not all of them are random. That's the credit card. Now then, what is the probability of randomly generating 16 digits? So there's no restriction, right? Repetition is allowed. What is the probability of getting your MasterCard numbers? Me specifically, 0. I don't have a MasterCard. Wait, I'm lying. I have MasterCard. Okay. The thing is that the probability will be for part A, my MasterCard. Okay, I have one number for my MasterCard, right? Suppose I have only one MasterCard, okay? Then there will be only one 16-digit one of the 16 digits combinations. But how many possible outcomes for the 16-digit MasterCard? Well, there are 10 digits for each place for 16 digits. So the probability of randomly selecting 16 digits from 0 to 9, 16 times, and it happens to be my MasterCard numbers, is extremely, extremely, extremely low. Now, part B. Receipts often show the last 4 digits of a credit card number. With only those last 4 digits are known, what is the probability of randomly generating other digits of your MasterCard numbers? My MasterCard, but 4 digits already known, right? 4 digits already known. So only 12 digits needs to be found. Okay, now part C. If you know that the first 4 digits are 6011, which is the Discover card, and you also know the last 4 digits of a Discover card. So of this 16 digit, the one known given, right? Known for the first four digits and last 4 digits. Then how many more digits needed? How many digits are unknown? There are 8 digits unknown, right? Now the probability the other 8 digits are guessed correctly. Somebody guessed the other 8 digits. That will be 1 over 10 to the 8, which is still a very small number, 1 with 8 zeros. What happened? Something's moving? Is something's moving? I feel like something's moving. Okay. 1, 2, 3, 4, 5, 6, 7. Okay, that's for number 26. I will give us a break, 20 minutes break. We will come back at next. We will do something to do with the quality control thingy, but let's take a look on the following example. For example, suppose we have uh, 10 markers, 10 identical markers, okay, and then let's say 5 of the blue, 3 of the red, and then 2 of the green. And then we want to select, we randomly select 3 markers. We randomly select 3 markers. Then how many ways can we select 3 markers? There will be 10 combination 3 ways. There will be 10 combination 3 ways. Now then part A. Well, let's see. We have 3 boxes now. 5 blue, 3 red, 2 green. And then we will select 3. And we want to see what is the probability that all 3 are blue. What is the probability that all 3 are blue? Then we see first how many ways can you select 10 markers from here. That will be 10 combination 3. Right? Now the thing is, if I need to select 3 blue, okay, so I will select 3 from here, nothing from here, nothing from here. Because I select 3 markers, right? I select 3 markers and all of them are blue, means the rest are 0. Okay, now then the question is how many ways can we select 3 blue markers? And that will be 5 choose 3 times, that's the 5 choose 3, 5 choose 3 times 3 choose 0. This is the 3 choose 0 times 2 choose 0. That's the 2 choose 0. So this will give you the probability of getting all blue. Now anything after this is just calculator. 5 choose 3 is, as I know, is 10. 3 choose 0 is 1. 2 choose 0 is 1 over, what is 10 choose 3? It's 10 choose 120. So that will be 1 over 12. Now let me change the problem now. Let me change the problem. What is the probability? What is the probability that 2 are red? Now, when we say the probability 2 are red, but we select 3 markers, don't forget. We select 3 markers. If I say 2 of them red, it also means 2 red and 1 not red. Is it right? Two red and 1 of them not red. So all of a sudden, the category actually becomes 3 red and 7 not red. Okay, now you want to choose 2 from the red one and therefore 1 from not red. Okay, now this then becomes 3 choose 2 times 7 choose 1 over and choose 3. Now let me slow down, let you think about it. The number of ways to get 2 red and therefore 1 not red divided by the number of ways to select 3 markers from these 10 markers. That's 3 times 7 over 120. That's 21 over 120. That's reduced by 3. Now, with this said, can you compute the following? And can you compute the following? Part C, find the probability to have 1 from each color. find the probability to get one from each color. Or D, find the probability of getting, let's say, one blue, which means the other two not blue. And then what is the probability of at least one green? Which means you need to do 1 minus probability of no green. Later on, the way you partition them, 2 green, 8 no green. Okay, let me give you 2, 3, 4, 5, 6, 7 minutes from here. Maybe 8, so 12:06. Okay, you try. 5 blue, 3 red, 2 green. And we want to select one from each. One from here, one from here, one from here. Okay, so how many ways can we obtain such result? That would be 5 choose 1 times 3 choose 1 times 2 choose 1 over 10 choose 3. That's 5 times 3 times 2 over 120. Which will be, what's that, 30 over 120? That's 1/4. How about probability of getting one black? Getting one black, let's do the blue, not one blue. So there are 5 blue, which means 5 not blues, right? Now, if you want to have one blue being selected, it means the other 2 must be not blue. The probability will be 5 choose 1 for the blue and 5 choose 2 for not blue. That's 5 times 10 over 120. That's 50 over 120. That's 5 over 12. Part A, what is the probability of getting at least one green? At least one green means 1 minus probability of no green. That is 1 minus. To get no green means nothing from here, 3 from here. That's 2 choose 0 times 8 choose 3 over 10 choose 3. What is 8 choose 3? 56. Okay, so that's 120 minus 56 over 120. That's 64 over 120. That's 8 over 15. Reduced by 8. Okay, now notice that A, B, C, D, E here is when we select 3 markers, and the event that we are doing, all of them regardless the order. Like 3 are blue, 2 are red, 1 from each, right? Doesn't matter the order, right? Okay, 1 blue regardless the order. Okay, at least 1 green. Okay, but you see, from the same situation, I can ask question in which the order is important. 5 blue, 3 red, 2 green. Suppose part F, I ask what is the probability when you select 3 markers, you get blue first, and then red, and then green. Blue first, and then red, and then green, in that order. Yeah, it seems like you get one from each, right? It seems like you get one from each, like part C. But this one from each color has no order, regardless the order, as long as you get one from each, regardless the order. Okay, regardless the order. Now, but in part F here, it has to be in that order. It has to be in that order. Then how do we do that? Well, we do it this way. We do it this way. Just do it one by one. What is the probability? The first one is blue. That's 5 over 10. What is the probability? The second one is red. That's 3 over 9. The probability the third one is green. That's 2 over 8. That's 1 over 24. Okay, so part G, for example, what is the probability that the first two are green, green, and then not green? The first two are green, and the third one is not. And what is the probability? The first one is green, that's 2 over 10. The second one is still green, is 1 over 9. And then the third one is not green. There are 8 not green. That's 1 over 45. Okay, now I think one of the events, two of the events that I don't want you to get confused is this. To get blue, and then red, and then green is not the same event to, one from each. When we say one from each, be blue and then red and then green is one of those events, but we have others. Okay, for example, blue first and then green and then red, or red first and then blue and then green, or red first and then green and then blue, or green first and then blue and then green and then red, or green first and then red and then blue. Okay, so when you make the order in that certain order, that's only one of the event of having one from each. When I say one from each, doesn't matter which one comes first, which one comes later, as long as I get one from each color. Okay, now blue and then red and then green is only one of that possible combinations. So you can expect, as you can expect, the probability to be in that certain order, in which, yes, you have one from each, but it has to be in that order, must be less than the probability of one from each order, regardless, one of each color, regardless the order. Okay, 1 over 4 is greater than 1 over 24. Okay, now the skill I teach you here, though, then being used for quality control. that's being used for quality control. Like what, Thomas? Let's say, for example, a wholesaler has a pack 100, let's say 100 calculators to sell. To sell to a retailer. Now, three of three of these 100 are defective. Three of them are defective. Now, the thing is the retailer randomly check let's say 4 calculators. And will reject if any, I think I will say will reject the batch, the whole 100 shipment of these calculators, reject the batch if any of these 4 are is defective. Any of these 4 is defective. So try to imagine this. There are 100 items, 100 calculators. You can make it 100 cell phones, 100 iPhones if you like. Okay. Now 3 of them defect. Therefore, 97 is good. Right? Now then, of course, when this batch come to the retailer will not know which of these calculators are defective. Okay. But the retailer, has a policy that I will randomly select 4 from this 100. Okay, I will randomly select 4 from this 100. If I find any defective from this 4, then I will reject the whole 100. Okay, now I say that this has something to do with quality control because this is basically, it is usually done. Why? Because to check all 100 calculators takes a lot of manpower. Okay, which may cut into your profit margin. And in fact, imagine if I change this 100 calculators becomes 100 phones, iPhone, let's say, or 100 Galaxy Notes. And when we say they are defective, we don't know what kind of defect they have. Not just cosmetic defect, right? Let's say some of the app actually not working right. Okay. And the thing is, in your phone, there are a lot of apps, in fact, a lot of hidden apps, right? Some of them not working well, but you will not know until you actually use it, right? Okay, so to check a defective phone, for example, takes quite a long time. Let's say 15 to a half an hour, suppose. Okay, now if you have 100 phones that you need to check, you want to check all of them, well, that translates into 50 hours. And if the minimum wage is $15, that translates into $750 spending to check this $100, right? It means you need to increase the price by approximately $7 or $8 each phone to sell, right? Thomas, I will not change my mind purchasing a phone if it is only $10 different. Yeah, but definitely it will reduce your ability to compete in the market, even though with just that $10 different. Okay. Now, not to say that if you find it to be defective, what you're going to do? You need to do the paperwork to return this and that, right? Okay. So you will see it may not be something you would like to do. And to be honest with you, checking a phone, for example, if it is defect or not, requires certain technical skill in which I don't think that person will be willing to accept a $15 per hour pay. No, this person needs to know plenty of things, right? His or her skill will be widely sought if that's how you want to do it, right? Okay, and the fact is now that people avoid doing it that way. Okay, so even if you have that skill, now they don't pay a lot because you know what? I don't check it. Okay, I will tell you further later on why the retailer will not check all of them. Okay, first because it costs too much, take a lot of manpower. Okay, but there's another reason why they don't want to do such thing. Now then, I continue from this situation. Find the probability that the whole batch is rejected. So basically, I return it. Okay, is rejected. But for that to happen, the probability that it is rejected is equal to the probability at least one defect. Right? The probability of getting at least one defect. Furthermore, to have at least one defect is the complement of no defect, probability of no defect. That's the situation, that's the circumstance that the whole batch will be accepted, will not be rejected. But under what situation that it will not be rejected? What is the situation if no reject? That's if all four that they randomly checked happens to come from here. And therefore nothing from here. Then what is the probability? The probability will be 3 choose 0 times 97 choose 4 over 100 choose 4. That's the probability. 97 choose 4, what's that? Now we start getting big numbers, right? That's 1 times 3, 4, 6, 4, 8, 4, 0 over 100 choose 4 is 3921225. That would be 1 minus, let me see, what's that? 3, 4, 6, 4, 8, 4, 0 divided by that number is 0 0.88361. That will give me 0.11639 probability of getting caught. So if I were the wholesaler, if I were the wholesaler and try to cheat my retailer, okay, try to cheat my retailer, and I sneak in three defective items, what is the probability that my retailer will catch it? The probability that I will catch that is, it's more than 5%. It's 11.6 something percent. So it's not a rare event, but the probability is also not that high. Okay. Now the thing is, will the retailer do so? Will the retailer use only, will the retailer only randomly select 4? And from the wholesaler point of view, will the wholesale dare enough to put 3 in there? Well, if I put 3 knowing that he will check 4, the chance I get caught is 11.6%. Let me change that to only put in 2 defect. Instead of 3 defect, let me put 2 defect. How will that change? What if I put only 1 defect? You see what I mean? Okay. Yes, I know. You may say, Thomas, that's illegal. It's already defective. Like, how can you sell it? Well, it is illegal if you know it. If you don't know it, then you cannot sue me, right? Okay. I know it's unethical, though. It is unethical. But think about it. How can I get these 3 defective calculators to start with? And very likely I get it from the manufacturer, right? Very likely I get it from the manufacturer. Well, Thomas, why you didn't check that? I have too many calculators I need to check. I sell to this one retailer only 100. Imagine how many calculators I have. Do I have to check all of them? No, I'm not spending my money that way, right? Okay. So uh, from here you see 2 point of view, from the wholesaler point of view and the retailer point of view. Okay, as a wholesaler, knowing the insider information on how many items will the retailer check randomly is a very useful information. That is an information that those who don't know math will overlook. Those who don't know statistics will think, you know what? So what if they check 4? They will not find it. Actually, if they check 4 randomly, the probability for them to find it is 11.6%. Not only I can say that it's possible, I can even tell you the probability. And those people who don't learn this, okay, they will think, no, the chance is small. But they cannot quantify it, okay? Because when we say it's a small probability, how small it is, that's still something you cannot quantify, right? Okay, when you say, oh, Thomas, I don't need to compute it, I just feel it. Now, the thing is, feeling is useful for you only, but feeling is useless when you talk to somebody, especially when you talk to me, right? You know that some bosses are really arrogant, right? But at the same time, don't forget, they can be a boss because they have so much experience, right? Such as when you say, oh, I feel this way, it's just like, I don't care about your feeling. I'm asking you, what's the probability? You know, what you feel and what I feel is different because what? This company is mine, it's not yours. So when you say small, the probability is small, that's because you don't take any risk. It's my company. You see the argument can be like that, right? Okay, the argument can be like that. Yes, I know some boss are so arrogant, but I want to say that some of them actually have reason behind it, though. Okay, when they say they actually have their capital in the company, and you still get your wage, your minimum wage, maybe. Okay, even if the company take the loss. So it may be easy for me as the worker there saying, oh, the probability is small, don't bother to find out, right? And then you as the boss will say, oh, for you it's small because when any loss happens, that's not your money, it's my money, right? So I care about the loss if it has to happen. Okay. Now then from wholesaler point of view is this, I already have these 3 defective. Okay. Maybe when I want to return it to the manufacturer, it's already past the warranty time. I get the items, I cannot sell it right away, so I keep it with me, right? Okay, but if I take the loss, there will be company loss. So I will try to pass the loss to the next person. Okay, yes, you may call that evil, but you may call that unethical, but the company is there not to stand on the ethical ground first of all. Okay, the first thing they need to do is they need to make money. Okay, I'm sorry to tell you this. As somebody who already worked in a big company before, I can say that ethics comes next. Okay, not that I say that all of them unethical. No, they try to do it ethical, but at some point when they think about it, you know what? Let's just do it this way. Okay, and I will tell you later on what I say, what you think is unethical is actually not so unethical. Okay, it has something to do with cost saving, which they try to pass to the customers. Okay, if I can save some costs, then I can actually keep the price low for the customer. Okay, so there's a reason for that though. So you may have a lot of ethical rules that you want to enforce on the company, but more or less later on you will see it will increase the price that that a company, a wholesaler in this case, will have to pass the cost when they sell the product. Okay, now let's see. Let's see. Let's go further. I will change that situation. I will change that situation. Instead of using calculator, now I change it to phones. So a company, a wholesaler again, a wholesaler has 100 phones to sell to a retailer. Okay, and the fact is, there are three defect phones. There are three defective phones that even the wholesaler doesn't know. So there are three defects, but even the wholesaler doesn't know which one. Okay, now for you to find all defective phones, of course you need to check all 100 phones, right? Just to find out three of them defects. Okay, now as I said, it will cost something, right? It will cost something. Okay, now when you send it to a retailer, do you think the retailer will check all of them? Like what I said earlier, if it costs the wholesaler to check that, then it will also cost the retailer to check that. Now, there's a chance that all these 100 phones are actually good. But then in between, when you send it to the retailer, you happen to use a certain company whose staff actually throw your stuff around and it messes up a little bit inside the phones. Okay, so it is possible the wholesaler actually send you 100 phones, good ones, but in its way to you, it kind of like get messed up. Okay, and by the time it reach you, something not right, but you still don't know what's wrong. Okay, now the thing is, will the retailer check? To tell you the truth, no, they will not check. Okay, usually in practice, this is what is being done. When I send these 100 phones to you, it comes with a warranty. Let's say it's 1 year warranty. Okay, and then the retailer basically have 1 year to to sell these 100 phones, right? Okay, will they check it? No. Why? Because of the following. Because of the following. The wholesaler send it to retailer. Okay, there's no quality control here. From retailer, they sell it to customer. No quality control too. They don't check it. They just sell it to you. They just sell it to you. What happened if the customers then found out that that phone is defect? You will return it, right? That's what the warranty for. So you see, instead of each one of them doing the quality control, okay, they actually not doing that. They just keep on selling it. They just keep on selling it until the customers, for sure, because you are the one using it, then more or less you will be the one testing it, right? And pray hard that if any defect, you find it in, let's say, 6 months. Then you have a chance to return it. Right? Usually it's a lot shorter than that though, maybe only 1 month, right? But imagine if they have to do the quality control here, they need to check all the phones. So let's say for this one already increased $10, and this one here already increased another $10. By the time it reaches you, because of the quality control, the price already increased by $20. Now, instead of doing that, they say, okay, I don't do the quality control. Both of these two groups, they don't do the quality control. They don't check it. They just send it to you right away. They just sell it to you because they know you will check that, right? You will check that. And that's how they pass the saving of $10 from here, saving of $10 to here, and it reach you. So will you say that it is wrong, they don't do quality control? Well, from the business point of view, it's actually a good thing because that way they can save money and the saving actually being passed to you. You will do the checking anyway, right? Regardless how much quality control they do, you will do the checking anyway. You will not say, you know what? I mean, think about this. However good quality control they did, however good quality control they do here and here, you will not buy that iPhones if there's no warranty at all. Nobody will take the company's word saying, you know what, I guarantee you, this phone is good. I don't need to give you warranty. Trust me, it is good. Will you trust that? I don't think so, right? In fact, the longer the warranty, the better. Okay, now you realize what's the warranty for. That's how they pass the cost to you, or to be more precise, that's how they pass the saving to you, so that they don't need to do too much quality control. Of course, they do some quality control in the sense, at least the one easy to see, like the cosmetic quality control. They look at the phone, it seems like the box is okay, so inside should be okay, right? Like iPhone, you never buy an iPhone not in a box, right? It must be inside a sealed box. Okay, so they seal it in a way such that it protects inside, and if the box actually get messed up, really messed up, if it's just a little bit, then nothing to worry. Okay, but if it's like really already bent in, let's say this is the box supposed to be, but it already bent in this way, and then this one like that, okay, then you start questioning, oh, you know what, maybe something fall onto this and it maybe cracked the phones inside, right? But 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 that's an easy quality control that takes a very short time. But really work with the phone and see if the app is defective or not takes a long time. And then rather you doing that, after all, you will do it anyway. And of course, if it's defective and you don't find it, then it's their profit, right? It's your fault not checking it right away, right? Okay. Now, believe it or not, that's the same thing with the cars that they produce. If you buy cars, it will be basically like that. Now, again, I'm not saying they don't do any quality control at all. No, that's not what I'm saying. Okay, I'm not referring to that. They do some quality control, but not too much detail. Okay, not too much detail. Okay, so even though, however much we don't like to get a lemon car, there's still a chance you get a lemon car. And everybody in the transaction actually being honest. Okay, because there's a chance that they check it already, it's working okay, but something happened in between uh, the transportation, the car being manufactured, let's say in Washington, by the time it reached LA, something happened in between, okay, such that the interior of what engine is messed up a little bit, or certain pin actually moved a bit too far. Yes, things can happen, right? Okay, so that's why the emphasis of quality control, even though it's getting better and better, there's no way we want to make it perfect, and the reason is it costs too much. Okay, you see, at least then when you do business later on, with that kind of mindset, you can explain to somebody when you sell something and it turns out to be defective. You will say it that way. You will defend yourself that way. You know what? If I have to check each item to the very details, it will cost me too much, and then I will end up passing the cost to you. How about I just do the visual one? I mean, a reasonable quality control, okay? And then when I sell it to you, I sell it with a warranty, let's say 1 month, okay? Let's say 1 month. So in 1 month, if you find anything wrong, bring it back. Okay, that way then I can save you some money because you will use it and check it anyway, right? Now, of course, if you say that to a customer without a statistic background, they may still yell at you though, but at least you have numbers on your side. What you did is economically, businessly reasonable from business point of view. Okay, see, I know some in the past when I did this kind of a talk, some students then say, but Thomas, it's still unethical. And I asked them, for those students who say it's unethical, I asked them, how many of you already worked in the company and have at least mid-level position? None of them say yes. Okay. In other words, they just know the theory that it is unethical, but they themselves never be directly involved or even own such company. Okay, and it is possible because of that mindset they will never have a company. It could be, you know. Okay, when you do business, you take risks. You like it or not. Okay. To be honest with you, when I uh, kind of like tell my in-law, my father-in-law, that what I do, I'm a professor. He said, "Why don't you do business?" Now that's because Indonesians. My wife is my high school friend, so yeah, long time already, huh? Yeah, my wife's high school friend from my hometown. So my father-in-law from the same hometown, and I know his mindset. We came from the same hometown. That you can only be rich if you do your own business and not working for other people. Okay. Now I'm not saying that he's materialistic. It's a very very reasonable question. That if my daughter get married later on, I want her to marry somebody who is financially stable, right? And if the inflation is high, then I would like that person to have enough capital, at least to have put my daughter in reasonable living. Okay, so no, I'm not saying bad things about him. I want to tell you his reason why he say that. Why don't you do business? Okay, why? Because business is basically the only way you can earn a lot of money in short period of time if you happen to do it, or you happen to have a good product that people want to buy. That's how you can make money. Okay, and asking for a company or a business person not to make too much money is actually unreasonable. Like if the company becomes really big, okay, you may see that the profit margin is small, but in aggregate, in total, they still make a lot of money. Okay. It's not, I'm not saying that I agree with what Amazon's doing. I'm talking about Amazon right now. I'm not saying that I totally agree with what Amazon's doing, that they make so billions of dollars. They make billions of dollars in how many years? In 1 year? Let's say they make 100 billion profit. Okay, but in 1 day, in 1 day only, they send, let's say, approximately 10 million items in just 1 day. In 365 days, in 365 days, multiply that by 10. Multiply that by 10. That's 3,650 million items. Okay, 3.6 billion items. And of course, it's not 10 million items per day. It's more than that, right? Okay. Now, think about what kind of items they sell. Let's say they sell, like, for example, my stage here, the desk I use for to put my laptop for me to teach here. This cost me $200. Do you expect them to make only $3 from this table? I don't think so. I don't think so. I don't think so. They're supposed to make at least $10 from here, right? Okay. Now, if for each item they make $10, then that's already 36 billion. Okay. Now, what happened if in between actually they make money from your subscription? They make money from you watching their videos. Okay. They make money from you renting their cloud. So on and so forth. Okay. So is this 100 billion profit is too much for them? And you will say, you know what, that's a ridiculous profit. Well, see how much items they actually move. They see how much they actually move the economy, how many people involved in this business. Okay. Again, I'm not saying that they are right, that I need to see further. I need to see further to pass that judgment. But I will not just say, well, if somebody make 100 billion profit, that's ridiculously too much. You know, until you are Jeff Bezos, for which you actually spend 20 something years to build that company. Okay. Don't pass that judgment yet. Okay. Not that I like him though. No, I still think that his Prime subscription should be lower, right? Okay, but that's how they make money. Actually, that's how they make money. Hey, you know what? This is America. You like it, you subscribe to it. You don't like it, you can walk away anytime. Right? Welcome to America. Oh, that's also the reason Amazon has that warranty, right? Oh, what happened? That's also the reason Amazon has warranty for the product you buy, because they know something can go wrong in between. Right? Something can go wrong from what they receive or what they send, so they give you the warranty. Okay. Now let's go on to the later part of this topic here, the topic of Mega Million, which is actually similar to the topic of Super Lotto. Super Lotto and Powerball. Different textbooks actually use any one of these three as their examples in their statistic and probability part. So let me ask you, if you are still paying attention, which one you would like to talk about? There will be the similar anyway. You choose one. I'm trying to show you that I'm not, I know this so well so that I don't need to prepare that in advance. Wow, I'm so good, huh? No, 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 no. I'm not that good. I'm saying that the concept is actually pretty easy, such that even you can understand. Okay, that's why I can explain this to you. I'm not trying to show off. No need. If I know my statistic or probability, I know my probability. I don't need to show it to you.
So we get to choose?
Yeah, choose one of them.
I guess the Powerball.
The Powerball. Today is Friday. Is it the Powerball day?
Oh, I'm not sure. I participated in that one.
Oh, okay, okay. Yeah. There was one time me and my stats class, I think sometime in winter 2016, the whole class actually purchased the Powerball because the jackpot was so high, and then each one actually put $2 in. We wrote the name. Yeah, too bad we don't get anything. And then when I reported to my department chair at West LA College, the department chair looked at me kind of mad. I said, I'm sorry. I mean, I'm not supposed to do this in class, right? Because we are not allowed to gamble. I mean, as person to person, like me and my students as friends, we can do it. The thing is, I use the time in class to collect money, even though I was not the one collecting the money, one of the students. So I and others, everybody in that class actually put $2 or even more and gave it to one student, and that one student went to buy the ticket, get the ticket, come back to class, and then we all took pictures and we all posted on Facebook just to make sure if we win, I have evidence that I have this ticket together with my classmates. Okay, we also took the pictures of the paper in which we all write our names that we purchased. These are the list of people purchasing these tickets, you know. So when I report to my department chair get mad that you Thomas, you should not do that. I say, I know, but you know what? I'm telling you because I'm close to you, but so if anybody report, just say that you don't know, okay? And there's no such thing. And then he say, no, Thomas, that's not what I'm saying. I'm saying you're supposed to let me know so that I can join. You know, so it's you call that a Powerball pool, right? Okay, hey, you know what? I tell you this: if we get that jackpot at that time, trust me, none of these students and me will go back to West LA College.
Right.
We were joking that we're supposed to have prenup, right?
The first job I worked at out of college, they always joked, oh, if they won the lottery, that they would just like quit, and they're like, oh, like I just would quit right then and there. And
but to be honest with you, even if I get the Powerball, right, I don't think I will quit. I don't think I will quit my job. Actually, because of this, I can get the money, but I may not be able to get my health insurance. You know, and the rule in our district is once I work for 20 years straight, I think 20 years straight, or maybe it doesn't have to be straight. As long as I work for 20 years, when I retire after that, I can keep my health care for the rest of my life.
Oh.
You know, that's the very good thing, right? Yeah. And I will pay part of my spouse health care, but which means part of that will be covered by them, by the district. You know, so if you think about it, dude, the older I am, my health care, if I pay it myself, will be more and more expensive, right? Why don't I just teach minimum so that I can keep my health care after 20 years teaching? Okay, so when I thought about it, I don't think that's what I will do. But of course, if you work for a company that does not provide such benefit, then of course quit. You know, okay. Now let's take a look on Powerball then. Let's see, where's my website? Give me a second. Powerball. What we need is how to play. Right, so let me click this Powerball website. This is a multi-states game. So let's see how to play. It should be somewhere here. Let me copy this first. Oh, not this one. This one here. I need this later on, but I still need how to play. Let me put this in our notes first. Yeah, I try to anticipate some students who don't know how this Powerball being played. Okay, let's see how to play. Huh? Oh, here. How to play. No, this is. Hold on. This is not Super Lotto. I mean, this is not Powerball. This is Lotto America, something else. I need Powerball. Powerball. How to play? Where's that? Yeah, because I know it's $2, not $1. Hey, where's that? Powerball. It's here. I'm still looking for how to play. Oh, here you are. Go back to our page. This is how to play. Powerball costs $2 per play. Now, what you will do is you will select five numbers from 1 to 69, and then one number from 1 to 26 for the red Powerball. So basically, they have two boxes. One box is the regular one. There are 69 numbers, and you need to choose 5 of them. Okay, and there's a Powerball number. There are 26 numbers there. You need to select one. Okay, you need to select one. Now, is the order important, Thomas, when you choose it? No, the order is not important. The order is not important. Now, the question is, what is the probability, if that's the scheme, what is the probability we hit the jackpot? Now, what is the jackpot? The jackpot is when your 5 regular choices and the Powerball match with what they get. So basically, you choose 5 plus 1 here, and they chose 5 plus 1 on the day. Okay, if they match all 6 of them, then you will get the jackpot. The thing is, how do they actually compute this probability? How do they compute that probability? Believe it or not, we already know how to do it. How is that being done? And we see it this way. From the regular box, there are 69 numbers. How many of them correct one? How many correct numbers from the regular box? 5 of them correct. 64 of them wrong. Okay, from the Powerball box, 1 of them correct, 25 of them wrong. So the first question, how many possible combinations you can use? The number of combinations. You can get. How many different slips you can get, choices you can get. That would be 69 choose 5 for the regular box times 26 choose 1 for the Powerball box. When you use your calculator to compute this, that's 69 choose 5 times 26 choose 1, which is just 26. Yeah, 26 choose 1 is just 26. That's how we get it. That's equal to this number. Oops. I want to move it. I can see it. Oh, I cannot move it. What's that again? Two nine two 20136 338. 292201338. Let's see our calculator again to compare. Okay, so that's the number of possible outcomes, right? The number of possible outcomes. Now, of those many outcomes, only one of them, only one of them is the jackpot. Only one of them is the jackpot. So that would be 1 over 292, 201, 338. Okay, which you see it matched with this. It matched with this. Okay, it matched with that. But that's for the jackpot only. The question of jackpot is actually quite common, even in every stats textbook though. Okay, it's quite common because all you need to do is actually count how many possible outcomes, and only one is the jackpot. But what we do here, what we just did, can only answer the top question. Can only answer the top question. What is the probability of jackpot? Now, what if I change the question to this? What is the probability that you get 3 regular correct and 1 the Powerball is correct? So what is the probability that 3 regular and 1 Powerball correct? Then how do we compute this? How do we get this 1 in something? Okay, how do we compute that? Then let's take a look on the setup again. There are 69 regular balls, 5 of them correct, 64 wrong. Of 26 Powerball options, 1 of them correct, 25 of them wrong. Okay, now if, so the denominator still 69 choose 5 times 26 choose 1, which will give us the 2,922,201,338 possible outcomes. Now the thing is, how about the numerators? Of course, it's definitely more than one way to get only 3 regular number correct and 1 Powerball correct. There's more than one way. So you cannot just say, oh, there's 1 on the top. No, you cannot. Now, how do we do this? Then think about it. How many regular ball I need to choose?
Professor, I
Yes.
think 292 million and not 2 billion.
Oh, yeah.
For
Am I? Oh, I have extra 2, huh? Thank
I
you.
think so.
Yeah, I have extra 2. Thank you. Ah, thank you. Thank you. Well, I have extra 2. 290. Okay, I have extra 2. I think down here. Yeah. Thank you. Okay, we will select 5 regular numbers, okay, but 3 of them correct. Only 3 from here, which means the other 2 has to be the wrong one. Now for the Powerball, we want 1 of them correct, so the rest is not correct. So the numbers will be 5 combination 3 times 64 combination 2 times 1 combination 1, which is 1, times 25 combination 0, which is also 1. How many ways can you select 0 from 25 items? You have 25 items. How many ways can you select nothing from there? One way. Don't select anything. Okay. 1 choose 1. There's only one way. You have only one choice. Okay. Now 5 choose 3. That's 10. How about 64 choose 2? That's 32 times 63. That's 2016. So this is equal to 20160 big over 292201338. Now the thing is, we want to write it in terms of 1 in what? So I want to have 1 here. And the question is, what will this be? Now to make the denominator becomes 1, I divide the top and the bottom by the numerator. Okay, that's how I get the numerator becomes 1. But what happened to the denominator? Now divide that number by 20,160. That's how I get that 1449411. In fact, I can go further. 14494.11399. Okay, so this 0.11 there in itself already rounded. They rounded to 2 decimal places. Okay. Now the thing is, what I show you here just now is a technique of computation that you don't find in any other textbook except in my class. But Thomas, do we need to know it? Well, if you can compute it, why you don't want to do it, right? Okay. What you don't want to happen is this: you know something, but you don't realize you know it, right? It's just like imagine if somebody asks you, "How do you get this?" Okay, and then, well, I know it, but I don't remember. Then, yeah. So it's the same that you say you don't know it, right? But from what I show you here, can you tell me that it's too hard? I don't think so. I don't think so. I don't think it's too hard. It's basically you break it into 4 boxes: regular correct, regular wrong, Powerball correct, Powerball wrong. Okay. Well, anyway, I think this is the end of your section 4.4. Your suggested homework will be from 4.4, starting from number 1 to number, I think from number 1 to number 31 is good enough. Yeah, do a little bit though, okay? But study from my old tests especially. Yeah, study from my old tests especially. Let me show you again where to find my old tests. Oh, beauty. Where to find my old tests? I'm recording this stuff. Yeah, my old tests. Go to harjuno.com. My name or my face. On the menu teaching, click previous teaching. Then go scroll down to ELAC College. Yeah, scroll down to ELAC College. And I strongly suggest you to study from test 1 on winter 14 or after. Winter 14 or after. Okay, the previous one is also okay. Let's say I randomly select spring 15, test 1. Now your spring 15 test 1, this one without solutions. So you will see, oh, the setup is not nice. Sorry, the setup is not nice. Let me choose the later one. Let's say from spring 17. I wonder if I posted. No, I remember spring 19. Yeah, spring 19 I posted. Yeah, right. Now I mentioned this before. My test 1 will look very similar to this. In fact, the first 1.5 page up to number 9, I can even say up to number 10, are same question, different numbers, except for number 10, maybe different wording, but the concepts will be the same, right? For number 1 to number 9, I will change the data only, but the question will be the same. I only change the data. Okay. Now the later part, chapter 3, page 3 and on, take a look on more of my previous tests. Okay. But keep in mind that the number of points for the test, for that question, tells you the maximum number of minutes you need to do that problem. So number 14, 3 minutes here, 3 points here. When you study to aim for to finish it in 2 minutes. But in your test, it should take you 3 minutes at most. Okay. Now this way, if it takes you, let's say 4 or 5 minutes to do that problem, then be suspicious that you kind of like miss some big idea. Okay. Yeah. That's for spring 19, but yeah, you can find others also. Let's say, I wonder if I have spring 18 up there. Yeah, I have spring 18 also there. Okay, just study from my maybe 3 or 4 sets of test 1 from ELAC College. Okay. Now going back to my class. Yeah, focus on your test 1, because in this test 1, if you don't do well, I may tell you to drop the class. Thomas, you're so harsh. No. I'm not trying to be harsh. I'm trying to help you. Pick your battle, right? If you don't do well in the easiest test, I don't think you can do well in the other tests. But Thomas, I can study more. Yeah, you should have studied more anyway, right? Okay. Now, let's see. Actually, we can talk a bit about probability right now. Okay, test 1 is the easiest one. You have test 2, actually the hardest one among 4, test 3, test 4. Okay. Now, your final average, according to my research, final average of, let's say, a total of 300 students. You can see from my old tests that I've been teaching this statistic so often, right? I have at least 300 data. Okay, of 300 students who has passed my class, none of them have final average greater than their test 1. Their final average always less than test 1, 100% of the time. So if your test 1 is 70, what makes you think your final average later on will be more than 70? It never happened. But Thomas, there's a chance, right? Yes, there is a probability you can be the first person. Okay, there's a chance, but when you compute the probability is so small such that in the last 13 years I teach statistics at West LA College and East LA College, that case never happened. Okay, is it possible that it happens to you first? Yes, it's possible. The probability is so small such that I will not bet on it. Okay, of course, if you don't do well in your test 1 and I say, if I were you, I drop the class. Let's say you don't drop the class. I'm totally fine. I have no problem with that. In fact, I prefer you to stay. Okay. I usually don't tell students to drop the class after test 1. Usually after test 2. After 2 tests, then I can make better judgment. Usually after test 1, I already know you have no chance. But I keep my mouth shut. Okay, because a lot of things can happen. I know. Right? That's why after test 1, I usually don't say that. But I think this semester I will start saying that. Why? Because I don't want you to waste your time on the class that you know you will fail and end up working too hard for something you know you're going to fail and it screw up your other classes. Okay? But of course, it's still up to you. As long as you attend the class, as long as you keep on saying here, I cannot drop you. Okay? Even if you get zeros in all my tests and quizzes, I cannot drop you as long as you attend the class. Okay, that's your right. The teacher cannot drop you simply because you don't perform in the class. Okay. Okay. That's why I think I said that on the first day of class that if you are in this class only for financial aid, then at least attend the class. Okay, by saying here in the discussion board. Remember I said that, right? Okay, I don't want to be too hard on you. Okay, but if your aim is only, I just want the financial aid, Thomas, then that's what you do. Okay. On the other hand, why do I say right now that if you don't do well in your test 1, I may tell you to drop the class? I hope by telling you this, you study a lot harder. Okay, it's not my interest. I don't have any benefit whatsoever if you fail your test 1. Actually, even if you pass it, I have no benefit. Okay, but it's about you, right? Okay, what should I do on my part so that you pass your test 1? Prepare you a lot earlier and give you such kind of warning. You better do well in your test 1. Okay? Yeah. How do we know that you are doing well in this class? Let me tell you what numbers you need to get. Okay? In your test 1, approximately 80. Okay? But once you get less than 70 points in test 1, this is bad. This is usual. I'm talking about passing students. Students who pass, they get around 80, of course, even more. Okay? But under what situation I call it bad if your test 1 is less than 70. Okay, now how about your test 2? What is the usual one? Believe it or not, the usual one is approximately 60. I will only say that you did poorly in your test 2 if you get less than 50. In other words, I will not give up on you even if you get only 55 in your second test. Of course, if your test 1 is less than 70 and your second test is 52 or 55, I will give you some big warning, right? Okay, but if you get 50 in your second test, I will say, you know what, you still have a chance. Okay, now the thing is for test 3 is pretty much the same, but from the history, it's better. It's better than this. Okay, in my test 4, however, people who get less than 70 usually don't make it. Okay, so try to aim for this. If all you want is just to pass the class, try to aim for this. Okay, I'm telling you this in advance so that you know I'm not just trying to make you happy if your test 2 gets 60. If your test 2 gets 60, I will say I'm happy for you instead of I'm not happy. Because what? I see people getting 60 end up passing the class. I see people getting 60 in the second test end up passing the class. Okay? But I almost see no one getting less than 70 in the first test. Actually, almost no one getting less than 70 in the first test pass the class. Definitely, if you get less than 68, you will not pass the class, at least from the history. Can good thing happens to you? Yes, yes. Okay, and that's why if you get around 68 in your first test, I will not say anything. I will wait until your test 2. But if you get less than 50 in your first test, that's a really a big red flag already. Okay, I think I will just let this class go right now, and next week I will hold my office hour the same time, 7:30. But I prefer you, if you have any question, do not wait until Friday to ask me that question. Okay? But my office hour next week will be from 7:30 to 8 o'clock only. The test will be posted, maybe I should say, the test is go public at 8:05. So 8:05, it's online, you print it out, okay? Or if you don't print out, you already have your blank paper ready, work on it, okay? You stop writing at 10:05 approximately, okay? And then you scan it, either you're using your scanner or your cam scanner or using your iPad maybe, okay? And then you post to Canvas before 10:20. It has to be fully uploaded before 10:20. And then lecture starts again at 10:30. Is it okay? So the way you did your quiz so far, okay, the way you did your quiz so far, it should be done. And like once you're done, you have to scan it, you take the picture, and then use cam scanner, convert that to PDF and upload it. Okay, make sure 10:20, before 10:20, it's already done. The system is being done in a way that if once the Canvas clock show 10:20, it will reject your work already. Okay, so the last time it still allow you to get posted is 10:19. Now, I am not saying you can start uploading it at 10:19. No, I'm saying that the upload should be done by 10:19. Okay, 10:19:59. Okay, once the clock shows 10:20, the system will not accept your file anymore. Okay, so when students say, Thomas, I don't know what happened. It takes so long. Well, come on. Okay, I don't know about your system. I don't know how you scan it. That's why I give you like 15 minutes to do it, right? But if you steal the time I gave you from 10:05 to 10:20, you still work there, you won't have enough time to scan and post it, right? Okay, you can blame the system, but the system is there so that it's fair. Okay, it's humanless, right? Okay, you have nobody to blame but yourself if you cannot post it online on time. Okay, that's my warning though. Okay, I tell you this not because I'm not happy with you. No, 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 no. I tell you this so that such things don't need to happen. I hope you understand it. Okay, there are things I cannot control, and this is one of them. I have to decide the time. But once I decide it, I cannot change it. Right? Why don't you give us more time, Thomas? I can give you more time and you still submit it late. So imagine if I change this to 10:30. Then what time you start working? 10:15? 10:20? Still, right? So that's not, the reason is not because I don't give you enough time. The reason is you just don't know when to start. Set your alarm. Okay, set your alarm. Now, don't forget that this class may be audited, and the good thing is everything is recorded online, such that when they audit me, they can see what numbers or what dates, what time I use, and if any students have their submission, posted after 10:20, then they will ask me, Thomas, why you are being unfair. That's why I do not accept submission by email. Okay, it has to be on campus for that particular test. Okay, please understand me on this one though. Please help me cover my ass, just like I try to help you cover your ass too. Okay, the test supposed to be only 2 hours. I give you more. Do you notice that? Right? I give you more. How do I give it to you? Okay, our class time is supposed to be from 8:20. If I give you 2 hours, then it should be 10 ends at 10:20. But it means you don't have enough time to print out and to scan. That's why instead of end later, I start early. You see? Okay, I start early so that the end for the test is still 10:30. Okay, yeah, that's for today. See you then next week.
All right, thank you.